Two of the most common avenues to practice logic skills are through computer science and through playing games. Today, my teammates and I have been given the opportunity to present what lies in between. My name is Shreya Dubey, and we will be showcasing an algorithm to solve Sudoku puzzles. For those who may be unfamiliar with the game, Sudoku is a logic-based puzzle game involving the placement of digits 1 through 9 on partially completed matrices of 81 squares. The modern version of the game is an altered rendition of its predecessor game, Latin Squares, which was first seen in French newspapers in 1895. The game then globalized, appearing in Japan in 1984, where it officially became Sudoku. The name was coined from a Japanese phrase which translates to "the digits are limited to one occurrence." This phrase pretty much sums up the rules of the game. Explicitly, the rules are: no digit should be repeated in each row or column or 3x3 grid of cells. This results in all digits represented in each row, column, and grid only one time. Once this is accomplished and all cells have been completed, the puzzle is beat. The naive approach to creating a Sudoku solving algorithm would be one that uses no logic to fill the cells, then checks the validity of the answers. This process is the true brute force approach, and serves to be inefficient and time-consuming. The worst-case time complexity of this approach is big O of 9 to the m if m is the number of empty spaces within the matrix. The best case would be big O of m. The alternate method is another kind of brute force approach done by using backtracking. This algorithm implements depth-first search to traverse back and forth between cells. The process of the algorithm is as follows. First, locate an empty cell, then try to place every digit 1 through 9 within the cell. Begin with the number 1 and check that it complies with all the constraints, or in other terms, the rules that were mentioned earlier. If any of the checks return false, move on to the next digit in the series. If all the checks return true, then the digit is valid in this spot and the process is repeated at the next empty cell. If you have reached the last digit and the checks return false, backtrack to the previously filled cells, change the values, and repeat the process. The worst case time complexity for this method is big O of 9 to the m. The best case is big O of m squared. Now, it's worth noting that the naive method performs better in the best case scenario in terms of time complexity. Though this is the case, the backtracking method calls for a substantially smaller amount of steps to reach a valid finished puzzle. Now here is Kyle to showcase a code and an example.
Thank you, Shreya. Okay, before we jump into the code, I'm going to show a rundown of what the backtracking algorithm will be essentially doing. Looking at the empty position where the arrow is pointing at, a number 1 through 9 needs to fill that position. Numbers 1 and 2 can't be used because it's in the same row or same column. So far, 3 is valid and can be used in that position. We insert 3 and move to the next empty position. At the next empty position, numbers 1, 2, 3, 4, 5, 6, 7, and 8 cannot be used since there are duplicate numbers in the same row, same column, or same 3x3 subgrid. So the next valid number that can be used is 9. We insert 9 and move to the next position again. Notice, at this position, we cannot use any numbers 1 through 9. Since we cannot move forward, we need to backtrack to the previous empty box because it was not the correct number needed for the solution. The number 9 was the only valid number that could be used for this empty box, so that must not be correct either. Again, we will backtrack. The number 3 needs to be reset since we cannot move forward when using it. The next valid number that can be used is 5, and I think now you can see how the backtrack algorithm will be flowing. So here, function defined as solved is how to implement the backtracking algorithm on the Sudoku board in a recursive manner. Starting at line 83, we're going to create a variable called find that stores a function defined as findEmpty. The function findEmpty is used to return the location of an empty position found. An empty position is indicated if there is a 0 in that position. Otherwise, the function will return none if there are no positions equal to 0. Lines 83 to 87 in the orange brackets If not, fine will return true, indicating a solution has been found because it will check if the board is completely filled. This is the base case of recursion because once we reach this case, it will be finished, meaning we have found a solution. Otherwise, find must have returned an empty position in terms of the positions row and column shown in else. Lines 89 to 96. First, we need to loop through the values in range 1 through 10, which will inclusively loop through values 1 through 9. Once we acquire a value, we will use it to see if it is part of the solution using if statements. Here's the function defined as valid. Essentially, this function is checking if the number used for an empty position is valid according to the rules of the Sudoku puzzle game. If the number found from the for loop passes as valid, we will add that value into the board. From this point on, we will keep moving forward to the next empty box with the new value added until we finish the solution. This will be done recursively to keep trying and trying until we find the whole solution or we've looped through all the numbers and none of them are valid. If this happens, we return false and backtrack to the last element that was just added. That element needs to be reset to 0 as an empty box since it is not correct, and try the for loop again. Here is a before and after of the solution output.